In this video, we're going to finish off Chapter 6, which was on relations. In particular, I want to talk a little bit more about equivalence relations and partitions. Some of the stuff I talk about in this video might overlap with what I talked about in the last lecture. I'm recording this in advance, so I don't exactly know how far we will have gotten at this point. But if it does overlap, then this is a bit of a review, and then we will, in the next video, we'll move on to Chapter 7. Okay, so let's talk a little bit more about equivalence relations and partitions. So first, let's just remember what it means for a relation to be an equivalence relation. So remember there was these three basic key properties to being an equivalence relation. The first of these key properties is reflexivity. So a relation is reflexive if every element of A is related to itself under the relation. I'm going to go through these fairly quickly, by the way, since these should be review from at least last lecture or the one before it. The second key condition is that it's symmetric. So a relation is symmetric if whenever x is related to y, then y is related to x. Okay. The way I'm writing it here is with a logical implication. So I'm writing that x, y being in the relation logically implies that yx is in the relation. This is the same thing as saying that whenever x is related to y, you also have that y is related to x. The third property is transitivity. So this says that if x is related to y and y is related to z, then x is related to z. Oops, I've got this wrong on the slide. Let me correct that. So this should say x is related to z. Okay, so I've written this again like a logical implication. But you should read this as whenever x is related to y and y is related to z, you have x is related to z. So you can kind of skip the intermediate thing, y. Okay, and we recall that R is called an equivalence relation if it satisfies all three of these properties. So reflexive, symmetric, and transitive. So you should also remember we had another special property of relations, which was antisymmetric. Antisymmetric is an important property of a relation, but it's not something that shows up in the definition of an equivalence relation. So you should always remember equivalence relation is reflexive, symmetric, and transitive, not necessarily antisymmetric. And I suspect that in the last lecture, we will have also talked about equivalence classes. So just to remind you, given some element x in A, where A is a set and R is a relation on A, an equivalence relation on A, and an equivalence relation R on A, the equivalence class of x is the set. So the notation is square brackets x, and this is the set of all y in A, such that y is related to x by the relation R. So hopefully you remember what this notation means, right? So I might switch between different notations as we go along, just so that you can get used to both of them. But y, r, x, remember this just means that y, comma, x is in the relation R. Okay, these two things mean exactly the same thing, so you should be used to both notations. And also to remind you what this means, so if you translate this into plain English, this means that y is related to x under R. So as an example, let's look at things related to Chapter 5, so this modular arithmetic. So we could define an equivalence relation. So let R be the relation on the natural numbers where x is related to y if x is congruent to y mod, let's say 7. Okay, so we can ask ourselves, what are the different equivalence classes here? And well, if you think about it, so if I take the equivalence class of the number 1, we get the set containing 1. So this should be all the, well, maybe I'll kind of explain it a bit slower. So this is all the y in the natural numbers such that y is related by r to the number 1. Or in other words, this is just the set of all natural numbers such that 1, or let's say, maybe I'll write it this way, so y is congruent to 1 modulo 7, which of course is just the set of all numbers containing, 1, 8, what's next? I guess 15, 22, ... So it's the set of all numbers of the form 7k plus 1 such that k is a natural number. Actually, k is either a natural number or 0. So notice that if I was to write the equivalence class of the number, let's say the number 15, well, this is also the same set, right? It's the set of things which are related to 15 under this relation is exactly the same as the set of things that are related to 1, because to be related to 15, you have to be equivalent or congruent to 1 modulo 7. So actually, the equivalence class of 15 is the same as the equivalence class of 1, which is the same as the equivalence class of, for example, 29, because it's always going to be, the set 1, 8, 15, 22, and so on. If that's not clear to you, then please do think about what this definition, what this relation is saying, and then you can probably convince yourself that this is true. So the other equivalence classes here, so we have the equivalence class corresponding to the number 2, 3, 4, 5, 6, and 7. So these are all going to be different than the equivalence class. So these are all going to be distinct, basically. So if I take, the equivalence class corresponding to 2, that's going to be not equal to the equivalence class corresponding to 3. But if you think about it, these 7 equivalence classes are all the different equivalence classes. Because basically, if you take an integer and I look at the remainder modulo, or the remainder when I divide by 7, the remainder is either going to be 1 or 2 or 3 or 4 or 5 or 6 or 0. And this class is going to be the set of all things, with a remainder of 1. This is going to be remainder 2, 3, 4, 5, 6. And then you have to be a bit careful here. So this is going to be the set of all things with a remainder of 0. Okay, so if you think about it, this equivalence class has sort of broken up the natural numbers into like 7 different sets. And these 7 different sets are completely disjoint. So, there can't be any number which is in this equivalence class and also in this one at the same time. So these have no common elements. Okay. And this is only one example, but this is kind of part of a general phenomenon that happens with equivalence relations. So what happens is that you end up getting, your equivalence classes are going to break up the set on which the equivalence relation is defined into disjoint pieces. So this is connecting now to the idea of a partition of a set. So a partition of a set is defined as follows. So suppose I let A be a set. A partition of A is a collection, let's write it curly p, of subsets of A such that, so first of all, the empty set is not in P. The sets in P have to be disjoint. So if, let's say, Q and R are in P, and they're not the same set, so Q is not equal to R, then they have to be disjoint. Disjoint means that they have empty intersection. So maybe I've never used this word before, I'm not sure. But if I haven't, this word means, or the word disjoint. So two sets are disjoint if they have empty intersection. So meaning that they have to be, if I look at Q and R, their Venn diagram looks like this. There's no common points, no common elements. And the third property is that for every element of A, there exists an element in the partition, so in P, such that X is in Q. Okay, so the way you should think about this is kind of like this. You've got some set A, and a partition just means that you're going to break up the elements of A into separate kind of classes. So you've got one kind of class, which is, let's say, the things in the yellow set. You've got the green set. I'm not sure if this picture is helping or not. But basically, you're kind of breaking up the elements of A into kind of classes. So then you've got the pink set, which might look like this. You've got the aqua set. I guess this color is called aqua according to PowerPoint. And let's say you've got an orange set. So basically the idea is, so these sets are all supposed to be disjoint. I know that in my picture I've sort of overlapped them, but there should be no overlap between the sets, and they have to cover all of A. And just to be clear here, I've drawn the pink set kind of disconnected, but you should think of this and this as being together being one set. Okay, so the point is, a partition is a way of breaking up the set into disjoint classes. And just a bit more terminology. So the sets of the partition, well, we can call them lots of different things. I think in the notes it says that they are called maybe cells or blocks or just the sets of the partition. But some people also call these things partition classes. There's all different kinds of terminology here, but hopefully it'll be clear from context what we're talking about when we talk about the sets of a partition or the cells or whatever. Okay, so suppose I've got a set A, which is, let's say, A, B, C, D, E. Okay, one partition. So the following are partitions of A. So if I take, let's say, the set containing the set A and the set B, C, D, E, so that's a partition. Or I could just take the set containing A, that's a partition, or the set A, B, C. So this, I should say, the set containing A, the set containing B, the set containing C, the set containing D, and the set containing E. Right? And the point here is that in each of these three examples, every element of A appears in exactly one set of the partition. So the following, so if I, so here's some examples which are not partitions. Of A. So for example, if I take A, B, C, D, E, A, this is not a partition because these two sets here are not disjoint. In other words, they have A is in both sets. And in a partition, your sets are supposed to be disjoint. Another non-partition is if I take, let's say, A, B, C, and just the set E. Okay, and the reason this is not a partition is because the element D does not appear. A third example is if I take the collection, let's say, containing the empty set A, and the reason this is not a partition is because it contains the empty set. So a partition cannot contain the empty set. One more example, if I just take, let's say, A, B, C, D, E, technically this is not a partition because this is just a pair of sets, okay? To make this a partition, it's supposed to be a set of sets. So to make this a partition, I would have to put the set brackets around everything. So this would be a partition if I had the set brackets outside, but the way I wrote it before is not technically a partition, at least according to the definition we're using in this course. Okay, so this, like I said, does connect to equivalence relations and equivalence classes. So kind of the thing I want you to take away from this is that basically, equivalence relations and partitions are basically the same thing. So what I mean by this is that if I have an equivalence relation, the equivalence classes form a partition. So the equivalence classes of an equivalence relation, I should say the set of equivalence classes of an equivalence relation on A, partition A. Well, I should maybe say is a partition of A. So let's kind of back up here. So the set of equivalence classes of an equivalence relation on A is a partition of A. And on the other hand, if you have a partition of A and you define two things to be equivalent if they're in the same cell, then that gives you an equivalence relation. So on the other hand, if P is a partition of A and we define R such that X is related to Y if X and Y are in the same cell of P, then this R that we get is an equivalence relation. And it's not hard to see this, right? Because think about the definition of an equivalence relation. So it will be the case that it will be the case that the relation is reflexive because every element is in the same equivalence class as itself. It's also symmetric because if X is in the same equivalence class as Y, then Y is in the same class as X. It's transitive because if X is in the same class as Y and Y is in the same class as Z, then X is in the same class as Z. Okay. So right, let's kind of prove a theorem which is going to explain this more formally. So this is called Theorem 6.10.3. And it says the following. So suppose that that A is a set and R is an equivalence relation on A, then, well, for any X in A, X is in the equivalence class of X. Secondly, for any x and y such that x is related to y, we get that the equivalence class of x is equal to the equivalence class of y. And thirdly, we get that for any elements x and y in A such that x is not related to y, so I'll write that as xy is not in the relation R, the equivalence classes of x and y have to be disjoint. The punchline here, the main purpose of this theorem is that this means that the set of equivalence classes is a partition of A. Okay, so this is the thing that I want you to really take away from this. If I take an equivalence relation and I look at the equivalence classes, that gives me a partition of A. Okay, so let's prove this theorem. Okay, so let's start by proving the first bullet point. So I want to prove that for any x in A, x is in the equivalence class of x. Now, if it's not clear how to prove this, then I would say you really need to review the definitions of equivalence relations and really kind of get your hands dirty with this concept, because this first bullet point should be very easy for you to prove at this point. So this all comes down to understanding the definition of the equivalence class and understanding what reflexivity means. So for the first bullet point, recall that the equivalence class of x is equal to the set of all y in A such that y is related to x under the relation R. Now, since R is reflexive, we know that x is related to itself. So therefore, by definition of the equivalence class, x is in the equivalence class of x. Okay, so like I said, this all just comes down to understanding the definition of equivalence class, and understanding the definition of reflexive. And remembering that an equivalence relation is always reflexive. Okay, so now let's prove the second bullet point. So suppose that x is related to y by R. So we want to show that the equivalence class of x is equal to the equivalence class of y. And we should remember that these two things are sets, right? So the equivalence class of x is a set, and the equivalence class of y is a set. So to show that the two sets are equal, what we can do is show that the equivalence class of x is a subset of the equivalence class of y, and the equivalence class of y is a subset of the equivalence class of x. Okay? Now to prove the first one of these statements, we have to pick an element of this set and show that it's in this set. Okay, this is really just reviewing all of your set theory proofs. So if you struggled with that part of the course, I think it's quite important to review it at this stage. So, okay, let z be any element of the equivalence class of x. And we want to deduce that z is in the equivalence class of y. Well, so since z is in the equivalence class of x, this means, apologies for the dogs barking in the background, that z is related to x. And now now what we know is that z is related to x and x is related to y. And now if we use transitivity, we can get that z is related to y. So by transitivity of the relation R, we have that z is related to y. So therefore, z is in the equivalence class of y by definition. And so that proves that we have this subset relation. So the equivalence class of z, or x, is a subset of the equivalence class of y. So therefore, what we've proven is this. Okay. For the other direction, we can do the same proof, except what I want to do is use the symmetry property once to change this x related to y related to x. So by symmetry, the symmetry property of R, we have that y is related to x. Now, if we follow, so I'm going to sort of skip a step here. I'll just say following the same argument as above, we can show that z being in the equivalence class of y logically implies that z is in the equivalence class of x. Okay, basically we want to do the same argument as above, except we want to use this instead of this. Okay, and when you do that, so this implies that, so therefore y is a subset, sorry, the equivalence class of y is a subset of the equivalence class of x. And now we've shown that one is a subset of the other in both directions, so therefore the equivalence class of x is equal to the equivalence class of y. Okay, so I would say that if it's not clear how to fill in those details, then again, you really need more practice with these definitions. So I'll kind of leave that to you to kind of think through the details of how can you apply the same argument as before to show this. And hopefully that's not too difficult. If it is, then like I said, it's really important to review these definitions. Okay, so we're not quite done here. We need to prove the third bullet point. So suppose that x is not related to y, and let's prove that their equivalence classes have, well, they have empty intersection. So in other words, this is saying that they're disjoint. Let's actually do the contrapositive. So for the third bullet point, we're going to use the contrapositive. So we show that if the equivalence class of x and the equivalence class of y have non-empty intersection, then that will logically imply that x is related to y. Okay? So in other words, I'm negating this statement and showing that it implies the negation of this statement, which is exactly how the contrapositive works, right? If we want to prove something implies something else, you can negate the conclusion and prove the negation of the premise. Okay, so if we're assuming this, what this means is that, so if I have these things having a non-empty intersection, so if this is not the empty set, then there's a point, there's an element which is common to these two sets. So this implies that there exists a z such that z is in the intersection of these two sets. So in other words, z is in the equivalence class of x and z is in the equivalence class of y. What it means for z to be in these equivalence classes is that z is related to x and z is related to y. Okay? Now, by symmetry of R, we can say that x is related to z, right? Because if z is related to x, which is what we wrote here, then x is related to z by symmetry. And now, by transitivity, we can combine these two statements that x is related to z and z is related to y to get that x is related to y. Okay, and this proves the contrapositive. Of course, the contrapositive is equivalent to the original statement, so we're done. Okay, so that completes the proof. Like I said, the thing to take away from this is that if I have an equivalence relation, I look at the equivalence classes, that partitions the set on which the equivalence relation is defined. And like I said before, so what we've proven in the previous theorem is that if I have an equivalence relation, it defines a partition on the set that the equivalence relation is defined on. But in the other direction, if I have a partition of a set, you can get an equivalence relation by just saying two things are equivalent if they're in the same class of the partition. Okay, so I hope that was helpful, and I'll see you in the next video. Okay, so let's start talking about chapter 7, which is functions. Like I said in the previous video, I'm pre-recording these things, so some of this might have been covered in the previous lecture or the one before it. But if so, then this is going to be review. If not, then you'll be seeing this for the first time. Okay, so let's talk about what a function is. Now, probably in your high school education, your high school math classes, you've probably learned some kind of an idea of what a function is. And what you learned in high school is not technically wrong, but it's not really going to capture the general definition of what a function is, more broadly than just functions of numbers. So let's talk about what a function really is. First, though, maybe I'll kind of remind you of the definition you probably saw in high school. So a function f can be thought of as a way, well, maybe not a way, but let's say maybe a machine. I don't know. So this is all very informal, but a machine for transforming an input x into an output f of x. So some of the types of functions you may be familiar with from high school are things like, f of x equals x squared minus 2x plus 1, or f of x equals e to the x squared plus cosine of x, or even maybe f of x equals the logarithm of 1 plus x, maybe absolute value of 1 plus x. So hopefully these kinds of functions are familiar to you. And in particular, probably in high school when you saw functions, you're probably familiar with functions where the input and output, so let's say the inputs and outputs are numbers, and the function is defined according to some algebraic formula. Okay, so in all of these cases above, when I take f of x equals x squared minus 2x plus 1, we're thinking of x as being a number, and then to get the output, we apply some algebraic operations, like we square the number, we minus 2 times the number, and add 1. This is what I want to sort of kind of communicate to you in this video, is functions are not all like this. So the input and output in general of a function do not have to be numbers. So these are things that you need to remember about functions, and they don't have to, a function doesn't have to have a nice formula. Okay, so I want you to I don't want you to forget everything you learned in high school about functions, because some of it is kind of useful. But I want you to broaden your mind about functions, about how you think about functions, to think about, a function is a way of turning an input into an output, but the input and output don't have to be numbers, and there doesn't have to be a nice formula. It's just any way of mapping each input to an output. And in fact, I want to define functions in an even more general or more abstract way than that. So here's a very abstract definition of a function. And whenever we talk about functions in this class, we always mean this sort of abstract definition. So a function, so let A and B be sets. A function from A to B, let's call the function f, little f. So a function little f from A to B is a relation from A to B. In other words, so this is just another way of saying a relation from A to B. In other words, it's a subset of A cross B such that for every element little a of A, there is a unique element little b of B such that A is related to B under the relation F, meaning the pair AB is in F. Okay, so I'm guessing that this is probably not what you thought a function was, but formally speaking, this is the definition of a function. So like I said, I don't want you to just forget everything you learned before, but I want you to, try to think about functions in this way from here forward. By the way, a bit of notation. So if f is a function from a to b, what we write is f with a colon, a, and then an arrow, b. So writing this means, so kind of translating this into plain English, this means that little f is a function from a to b. So we're going to need a whole bunch of other definitions here. So some more definitions. So first of all, given an element, let's say A in A, the unique B in B such that the pair AB is in F, we call that the image of A under F. Okay, or in other words, we define B to be F of A. So the notation here is we write F of A equals B, and that means that B is the image of A under F. Okay, so I'm going to keep on giving you more and more terminology and notation, but then we'll look at some examples, and hopefully some of these concepts will become a bit more clear as we look at more examples. Okay, so another thing I want to define is, so if f is a function from a to b, we call A the domain of f, and we call B the, well, you might be guessing right now that I'm going to say range, but I'm not going to say range. So B is called the codomain, and there is a difference of f. So this is not the range, not necessarily the range of f. It's not that common of a terminology, but in this course, sometimes we call it, we can also call B the target of f. But probably when you take courses in the future, they'll probably call it the codomain. But often in the notes, the way the notes are written, sometimes they use the word target. So you should know that the domain, codomain, or the target, so these are synonyms for each other. Now, okay, this is the domain and codomain. What's the range? Well, the range is the set of all elements of the codomain which are the image of some element of the domain. So the set of all elements of the codomain B which are images of elements of the domain. So notationally, what we're saying here is that the range is the set. So the notation we're going to use is RNG of F, and that's the set of all B in B such that there exists little a in A such that F of A is equal to B. Okay, so it's the set of all things which are images of elements of A. Okay. So I realize that this is a lot to take in, and it's kind of tricky because you have learned about functions before, but you probably didn't learn this terminology, and you probably didn't learn what a function is in this kind of general context. You certainly probably didn't learn that a function is a special type of relation. So this might be a little bit tricky to grasp at first, But let's look at some examples. So kind of the simplest way in most cases, so a simple way to define a function f from a to b is to specify the image of each element of A. And this is probably the type of function definition you're used to, right? So for example, we can say let f, so with the domain being the real numbers and the codomain being the real numbers, so let f be the function from the reals to the reals, so such that f of x is equal to x squared for all x in the real numbers. So this is a perfectly valid definition of a function, right? So what I've done here, so I haven't defined the function as a set of pairs. So I haven't really, it doesn't look like I've defined a relation here, but I have, because this is specifying, so this is saying that for every x, it's saying that the image of x is x squared. So this is enough to tell me what the function is. So if I wanted to write f as a set, or as a relation, in other words, f is the set x comma x squared for all x in the reals. Okay. So let's just play with some of these definitions. So the image of, let's say, 3 is, well, it's f of 3, which is 3 squared, which is 9. So in particular, 3, 9 is in f. The image of -4, for example, is 16, right? So in other words, the pair -4, 16 is in f. Or in other words, f of -4 is 16. Okay, so these are all things, I guess, that you're used to, but yeah, it's kind of important to formally understand what these definitions are saying. What's the range now? Well, I'll tell you what it's not. So the range is not, the range of f, this function f, is not R, okay? So R, the real numbers, is the codomain, but it's not the range. So it's the codomain because it appears on this side of the function definition. So this is my codomain. This is terrible writing with a highlighter. But yeah, it's not the range because, so the reason it's not the range is because you can't get -1, for example. So -1 is not in the range of f. So there's no real number that I can square to get -1. So the range of f is actually all of the non-negative real numbers. So the range of f is the set of all y in R such that y is at least 0. So we can write that in sort of interval notation as the interval between 0 and infinity. So this means, this means the same thing as this. So it's all the numbers between 0 and infinity. I'm not sure whether we're introducing this notation or not in this class, but in any case, so the square bracket here means that y is at least 0, but it could be equal to 0, and this round bracket here means that y is less than infinity. So it's all the numbers between 0 and infinity. But in other words, probably a better way of writing this, if we're not going to define this interval notation, is to write it like this. So this is the range of this function, because for each element in this set, there's something that it has a square root, basically. So for example, if I take y in this set, then square root, it has a square root, and if I square the square root, I get y. So y is the image of some element of the domain. I also want to define something called the preimage of an element. So this is another definition. So let f be a function from a to b. We say that, well, so for an element b of b, we say that a is a preimage of b if f of a is equal to b. Now, here's a thing I really want to stress here. The preimage, well, or maybe I shouldn't even say the word the preimage, because there isn't just one preimage for each element. So preimages are not unique. In other words, some b and b, little b and big B, may have more than one preimage. And in fact, it may have zero. So some elements of B have no preimage. In fact, that's sort of related to the definition of the range, right? So the range of f is equal to the set of all b and b, such that b has at least one preimage. So this is a completely equivalent definition of the range of f, right? Okay, so let's go back to this example. For example, when we had f of x equals x squared, where f maps from the reals to the reals. So the preimage of the number 4 is, well, there isn't just one. So actually, don't write this sentence as I've started it here, right? There is no the preimage, okay? So maybe I'll say the preimages of 4 are the numbers -2 and 2. Because, and the reason is because f of -2 is 4 and f of 2 is 4. So -2 and 2 are both preimages of 4, and so in particular there's 2 of them. And if I take the number -4, for example, so -4 has no preimage, or let's say preimages, because there's no number that I can square to get -4. Maybe I should be clear here. When I say there's nothing you can square to get -4, I mean that there's nothing in the domain, which is the real numbers, that I could square to get -4. However, if the domain was the complex numbers, then -4 would have a preimage. The preimage would, in fact, it would have 2 preimages, 2i, where I is equal to square root of -1, and -2i. So maybe I'll do that as an example. So if we take f from the complex numbers to the complex numbers such that f of x is x squared, then the preimage of, let's say, well, the preimages, I should say, so I keep on making that mistake. The preimages of 4 are still -2 and 2, and now the preimages of -4 are -2i and 2i, because if I take -2i squared, I get -4, and if I take 2i squared, I get -4. So here, I is defined to be the square root of -1. Okay, so hopefully these definitions are a bit more clear. It's going to take some time to get used to these things. In particular, let's do another example where the function is not defined in terms of some simple formula, and where the domain and codomain are not just sets of numbers. So let A be the set of all students at UVic, and let's say I let B be the set of all classes at uvic. Okay, and I can define f to be a function from a to b. So I'm going to say define f from a to b to be the function such that for each x in A, f of x is equal to student x's favorite class. So student x's favorite class. Okay, so hopefully it's clear what I mean by that. Maybe this notation is not the most formal, but basically what I'm saying is for each student, f of that student I define to be equal to that student's favorite class. So if Bob is a UVic student whose favorite class is Math 109, then, well, there's a few things that we know. So the pair Bob, comma Math 109 is in F. Or in other words, this means the same thing as saying f of Bob equals Math 109. Math 109 is in the range of F. Bob is a preimage of Math 109. Okay, so all of these statements are true. And this is a function, right? Because for every input, so the inputs are students, and for every input, there's exactly one output. So each student has just one favorite class. So this is a function. Okay. Yeah. So here, by the way, the codomain is equal to B, the set of all classes, and the domain is A. Okay. Now, to figure out the range, in this case, it's pretty difficult because you have to go through every class and find one student. Well, for every class, I want to check, is there a student whose favorite class is that class, right? If there is, then that class is in the range, and if not, then it's not in the range. So I'm not sure, is Math 122 in the range? So if for one of you, this is your favorite class, then Math 122 is in the range. And if nobody's favorite class is Math 122, then it's not in the range. Notice here that this is an example where the domain and the codomain are not sets of numbers, and there's no nice formula for computing f of x for each input x, right? So if I give a student as an input, there's no formula that tells me that student's favorite class. So functions do not have to have simple formulas for algebraically determining the value of the function. So let's look at just one more kind of complicated example, which relates to some of the number theory definitions we had before. So, for example, let's say G, or maybe let's use a Greek letter. So functions don't have to be called f. So you can call a function something else. So I'm going to define phi to be the function from the naturals to the naturals, be the function such that f of n is equal to the cardinality of the set of all natural numbers d such that d divides n for all n in the naturals. Okay, so you can see that, I mean, technically this is a function, right? So for every natural number n, I can define the set of divisors of n, and you can take that set and compute how many elements it has. So this is a function. Oops, sorry, I should have defined, I started by calling the function phi, and then I wrote f. My apologies. So this should be phi of n is equal to that. So this is a function. And in some sense, this does have a simple, I mean, this is a sort of formula for phi of n, but you can see it's not a very simple formula. And it's not just some sort of algebraic thing that you can compute really easily. It's a kind of complicated function. But that's, you can still compute this function. So if I take phi of 7, that's going to be 2 because 1 and 7 are the only positive divisors of 7. Or if I take phi of 1, it's just 1 because 1 is the only divisor, positive divisor of 1. So if we think of phi as a relation, we would say that the pair 7, 2 and the pair 1, 1 are in phi. Okay, to be honest, in most cases when we deal with functions, we will probably just define them by specifying the image of each element in the way we have here. So by writing phi of n equals some sort of formula. But you should also realize that a function, formally speaking, is a relation. So it's a set of pairs in A cross B, where A is the domain and B is the codomain. Let's spend a few minutes now talking about what it means for two functions to be equal. And if you think of functions as sets, then you already know the answer to that, right? Because we know that two sets, x and y, are equal if, any element in the universe is an element of x, if and only if x is an element of y. If I have two functions, so if f and g are functions, it's kind of the same thing, right? So in particular, functions are sets, right? Then f and g, they are sets. So f equals g kind of, as functions, means the same thing as f equals g as sets. So if and only if the sets, so we define f to be equal to g if and only if, by the way, this if double f, in case you haven't seen this before, this means if and only if f and g are the same set. But to be a little bit more careful here, let me give you an equivalent definition. So two functions, f and g, it turns out, so they're equal. So it turns out that this set definition given above is the same as the following definition. So if they have the same domain, they have the same codomain, and f of x is equal to g of x for all x in the domain. Okay, so this turns out to be the same as saying f and g are the same set, but probably in most cases this is going to be a more useful definition. So if you're ever asked to prove that two functions are equal or to show that they're not equal, then you should probably use this definition. So if you're showing that they are equal, you have to show that they have the same domain, they have the same codomain, and that f of x equals g of x for all x in the domain. If you're showing they're not equal, then what you have to do is show that one of these things fails, right? So either they don't have the same domain, they don't have the same codomain, or they don't assign the same value to every x in the domain. Okay, as a few examples to kind of illustrate this, suppose I take f to be the function from R to R such that f of x equals x. I take g to be the function from the integers to r. So this is, I should say, f of x equals x for all x in r. So I could define g to be a function from the integers to the reals, such that g of x is x for all x and z. Let's suppose I define, or say I try to define h to be a function from the reals to the integers, such that h of x is x for all x in r. So it kind of feels like these three things are functions, and it kind of feels like they're the same function, right? Because all of these functions are saying f of x equals x, g of x equals x, and h of x equals x. Now, here's the thing. So let's start with the third function, or I should say in quotes, function h. I should point out here, h is not a function. So the reason is because a function must have the property that every image is in the codomain. But the problem is the image of the number 1/2 is like, h of 1/2 is a half. And this is not in Z, which is the codomain. So therefore, h is not a function. Now let's talk about f and g. So f and g are functions. You can kind of check the definition of function. So if you think of them as relations, you can see that they are proper functions. It might seem like they're equal, but they're not equal. So they're not the same function. They're not equal because they have different domains. So the domain of g is the integers, whereas the domain of f is the reals. So if two functions have different domains, they can't be the same function. Also, if I defined, let's say, j to be the function, let's say from, well, z to z, by, again, j of x is equal to x. Again, j is not the same function as f, and j is also not the same as g because it has different codomain as from g. Okay, so this concludes this video, and I'll see you in the next one. Okay, so let's continue in chapter 7 on functions. In this video, we're going to talk about some special types of functions called injective, surjective, and bijective functions. It might not be so clear why we care about these things right now, but later in chapter 8, these things are going to be extremely important. So you've got to try to get these definitions under control. Okay, so the first definition. So we say that a function f from a set A to set B is injective if any two different elements of A have different images. Okay. In other words, a function is injective if whenever x is not equal to y, that logically implies that f of x is not equal to f of y. So this is, of course, for x and y in A. So in other words, yeah, so like this says, if x is not the same as y, then f of x is different from f of y. The contrapositive of this, of course, is that, that f of x equals f of y logically implies that x equals y. Maybe I'll move this x, y, and a above. Okay, so a function is injective if different elements of A have a different image under f. So in other words, if x is not equal to y, then f of x is not equal to f of y. Or the contrapositive, if f of x equals f of y, then x equals y. Another terminology for this is, so we sometimes say, instead of injective, 1-to-1. So if I say that a function is 1-to-1, that means the same thing as injective. Okay. And alternatively, we sometimes use the word injection. So if we say, we might say f is an injection, that just means that it is injective, right? So all these things mean the same thing. F is injective, F is one-to-one, or F is an injection. Yeah, it all means the same thing. Okay, let's look at an example. So for instance, suppose let f be the function from the reals to the reals defined by f of x equals 2x plus 5. Okay, so if you look at the function, if you plot it, it's a straight line, right? It's a straight line where the y-asymptote is 5 and the slope is 2. So it's kind of a somewhat steep line. Okay. So I claim that f is injective. So I want to say that any two different real numbers have different images under f. Or in other words, if two numbers have the same image under f, then they must be the same number. To prove this, I want to go back on the previous slide to this definition, or this statement here. So we said that a function is injective if it holds that whenever f of x equals f of y, then x equals y. In a lot of cases, this is the easiest way to show that something's injective. So in this case, what I would do is, so here I'm claiming f is injective. Here's the proof. So let x and y be real numbers. In other words, let x and y be in the domain of f, right? The real numbers. And suppose that f of x equals f of y. And we want to deduce that x is equal to y. And in this case, it's going to be pretty easy, right? Because you can take, so if f of x equals f of y, that implies that 2x plus 5 equals 2y plus 5. Now, if I subtract 5 from both sides, that means that 2x equals 2y. And now if I divide by 2, I get that x equals y. So what I've demonstrated is that whenever f of x equals f of y, x must equal y. Okay, so that actually proves that this function f is injective. Okay, let's look at an example of a non-injective function. So let's take, for example, so let f be the function from the reals to the reals defined by f of x equals x plus 4 squared. Now, I'm going to show that this is not injective, but you should be able to kind of recognize when a function is injective or not. One way to recognize that, if you have a function like this where you can plot it pretty easily. So if I plot this function, we've got that at -4 it's 0, and it's a kind of quadratic function. It has only one root at -4, so it kind of goes like this, right? It's a parabola. How do I know that this is not injective? Well, the point is that if I take, the question of whether a function is injective is, are there two different values which have the same output? And here we can clearly see that there are, because if I take a sort of horizontal line here, it cuts through the function twice. So if I kind of take this to be my x and this to be my y, then definitely, so f of x is equal to f of y. Now, I want to clarify that this is a picture. This is not a proof, because in particular, I haven't proven that the function even looks like this, although we sort of know that it does. To really prove that this is not injective, what we need to do is give a counterexample. So I'm claiming that f is not injective, or maybe I'll use the other terminology, f is not one-to-one. Okay, so my proof is by taking a counterexample. So for example, suppose we take x equals -5 and y equals -3. And I've chosen that kind of carefully, or specifically, so that I know that the f value at these numbers will be the same. I chose them to be on opposite sides of the number -4 over here. So just like in the picture. So if I take f of x that's negative 5 plus 4 squared, which is negative 1 squared, which is 1. And if I take f of y, I get negative 3 plus 4 squared, which is 1 squared, which is 1. So f of x equals f of y, but x is not equal to y, so it's not injective. Okay. Or in other words, it's not one-to-one, right? Remember, one-to-one and injective mean the same thing. Okay, let's look at another example. So suppose I take the function, f from 0 to infinity, the interval 0 to infinity, to the interval 1 to infinity. So by the way, I'm not sure whether I've ever introduced this interval notation, but generally speaking, if I have the interval AB, that's the set of all x and r such that x is between a and b, strictly between them, so not equal to a or b. If you take some square brackets, that means x and r such that x is between a and b and might be equal to them. If you take partially square brackets, that means a similar thing. So and maybe for completeness, I'll draw the last one. So if I take this, it means this. So x is greater than a and less than or equal to b. Okay, basically when I draw these intervals, it means all the numbers between a and b, where if there's a square interval on one side, it allows you to be equal to that number. And if there's a round bracket, then you have to be strictly greater or strictly less than that number. When you do that with infinity, so if I write, say, 0 to infinity, or generally if I write a to infinity, that's the set of all real numbers such that x is bigger than a and less than infinity. Or in other words, every real number is less than infinity, so you can just write that x is bigger than a. By the way, never write this, something like, I don't know, a to infinity, including infinity, right? So this part doesn't make any sense, right? Because infinity is not a real number. So you can't include infinity in your set. Okay, so back to the example. So let f be the function from this set to this set, such that f of x is 1 plus 1 over x. So I claim that it is injective. So suppose f of x equals f of y for some x and y in the domain of f, so between 0 and infinity. Then what we get is that 1 plus 1 over x equals 1 plus 1 over y, which if we subtract 1 from both sides means that 1 over x equals 1 over y, which implies that if I multiply both sides by y and multiply both sides by x, I get that y is equal to x. And so f of x equals f of y logically implies that x equals y, so therefore it's injective. Now, one thing that's worth mentioning is that if you have a function that's not injective, you can sometimes turn it into an injective function by restricting the domain. So if we go back to this example here, remember this parabola, this quadratic function, x plus 4 squared, is not injective when the domain is the set of all real numbers, right? So when the domain is the set of all real numbers, you can plug in -5 and -3, and they both give you the same f value, so it's not injective. However, if you look at this picture, if I was to kind of keep this half of the graph over here, but somehow delete this half of the graph, then it would be injective. So if I took f from, with the domain being -4 to infinity to r, such that f of x is equal to x plus 4 squared, then this is injective. Because you no longer have two different values that have the same output. Let's actually do this as an example. So in case this description wasn't clear. So let f be the function from -4 to infinity to, let's say just to the reals, be defined by f of x equals x plus 4 squared. So I claim that f is injective. So even though it looks like the same function we had before, and before we said that this wasn't injective, now that I've changed the domain, it will be injective. Okay, so let's suppose, so the way that these injectivity proofs usually work, if you're trying to show something is injective, let's suppose that x and y are in the domain, so they're between -4 and infinity, and that f of x equals f of y. So this means that x plus 4 squared is equal to y plus 4 squared. Okay. Now the way that these things work is that if something squared is equal to something squared, that implies that the absolute value of that thing, so the absolute value of x plus 4 is equal to the absolute value of y plus 4. Now here's where the domain comes in. So everything I've written so far would have been true even if I had the domain being all real numbers, like we had before when it wasn't injective. But now the difference is, now that the domain is only numbers which are at least as big as -4, we can say that since x plus 4, or sorry, x is at least -4, we know that x plus 4 is at least 0. So the absolute value of x plus 4 is just equal to x plus 4. That's how absolute values work, right? Similarly, y is at least -4, so absolute value of y plus 4 is equal to y plus 4. So therefore, since we've already proven that the absolute value of x plus 4 equals the absolute value of y plus 4, and we've proven that absolute value of x plus 4 is just x plus 4, and absolute value of y plus 4 is y plus 4, we can put this all together to get that x plus 4 equals y plus 4. Therefore, by subtracting 4 from both sides, we get that x is equal to y. Okay, so this function is injective. So this is a bit of a lesson to you that if you're trying to check if a function is injective, the domain is very important. Okay, so now we're going to look at the next definition, which is surjectivity. Definition: a function f from a to b is surjective if for every y in b there exists x in a such that f of x is equal to y. Okay. So in other words, a function is surjective if the range of f is equal to the codomain of f. Okay, another terminology for this is either that we sometimes say f is onto, so onto means the same as surjective, or that f is a surjection. So if you ever hear the word onto, that means the same as surjective, or if somebody says that a function is a surjection, that also means the same as that the function is surjective or onto. Or the same thing as saying that the codomain of f is equal to the range of f. So if you forgot these words like codomain and range, I suggest reviewing them from the previous video. Okay, so let's look at one of these examples again, but this time from the perspective of surjectivity. So suppose I let f be a function from the reals to the reals be defined by f of x equals 2x plus 5. So I claim that this is surjective. So to prove this, what we need to do is show that every element of the real numbers, which is the codomain of this function, so every element of the codomain can be written as f of something in the domain. Or in other words, we want to show that everything in the reals is in the range of f. So let y be any real number, and we want to show that it's in the range of f, so we want to find some x such that f of x equals y. Now, it's pretty easy to figure out how to do that. I mean, so this is a kind of side calculation. So if I wanted to have f of x equals y, what I would want is to find an x such that 2x plus 5 equals y. So if I solve for x, that tells me that x is y minus 5 over 2. Okay, so this gives me some idea of which x I should pick. So let x be equal to y minus 5 over 2. So then f of x is equal to 2x plus 5, which is 2 times y minus 5 over 2 plus 5, which, unsurprisingly, since I set it up like this, is equal to y. Okay, if you do the algebra, you'll see that this simplifies to y. So therefore, y is in the range of f, and so this is true for every real number y, so therefore f is surjective. Okay, now when you're talking about surjectivity, your domain and your range are going to be really important. So as an example, just a small tweak of that example from the previous slide can give you a function that's not surjective. So for example, if I change the domain and codomain to be the integers, so let f be the function from the integers to the integers defined by f of x equals 2x plus 5, you might think, okay, this should be surjective too, because 2x plus 5 was surjective on the previous slide when we went from R to R, so why shouldn't it be surjective now? But it's not surjective, okay? Because, for example, so this is, so like I said, it's not surjective. And the reason is that you can't actually get every integer by applying f to some integer. So it's not the case that every number is in the range of f. So for example, a key thing here is that for any, let's say, x in the integers, if I take f of x, so that's going to be 2 times x plus 5, this is always going to be odd because it's 2 times a number plus 5, okay? That has to always be odd. So in particular, the number 2 is not in the range of f because there doesn't exist x in the integers such that f of x is 2. Okay, so this is just trying to illustrate the fact that the domain and the codomain are really important when you're dealing with surjectivity. Okay, let's consider another example. So suppose that f maps the reals to the reals such that f of x is x plus 1 squared minus 1. So maybe think for yourself, is this onto? Is f onto? So onto means the same as surjective, remember? Well, let's think about plotting this for a second. So, I'm not going to plot this really precisely, but basically like the minimum point of this parabola is at -1, and the minimum will be -1. So it's some kind of a parabola like this, right? That's probably horrible. I'm going to plug in 0, it should be 0. So maybe I'll draw it a little bit more accurately, and maybe it looks something like this. Okay, I think this is still terrible, but whatever. Okay, so is this onto? Well, I think it's clearly not onto, right? Because, how am I, you can see the minimum point is at -1. So it's impossible, for example, to plug in a value and get -2. So the answer is going to be no here because there does not exist x in the real numbers such that f of x is equal to -2. So therefore, -2 is an element of the codomain, which is not in the range, so it's impossible. Now, I haven't really justified this, so and you should always remember you need to justify things properly. So here's a proof of this fact. So suppose that x is in R and x plus 1 squared minus 1 is equal to -2. So then x plus 1 squared is negative. So if I add 1 to both sides, I get x plus 1 squared is -1, but the square of a real number is always at least 0. So this is a contradiction. So one sort of symbol for contradiction is two arrows pointing at each other. So that's what I'm using here to say this is a contradiction. Okay, so this function is not surjective. However, notice that if I was to change the function a little bit by changing its codomain, you would get a surjective function, right? So if I was to modify this by changing this r here to the interval -1 to infinity, then this would be surjective. Okay, so again, the domain and the codomain are important for understanding if a function is surjective. Okay, now let's add another definition, which is going to be basically just a combination of the previous two definitions. So definition, a function f from a to b is a bijection if it is an injection and a surjection. So we also say, so kind of other terminology, we could say that f is bijective or f is a one-to-one correspondence. I don't love this terminology because it kind of sounds so similar to being one-to-one. So remember, a function is one-to-one if it's an injection or injective, but this is saying it's a one-to-one correspondence if it's bijective. Okay, so it's important to keep that clear. One-to-one is not the same as being a one-to-one correspondence, right? One-to-one correspondence means that you're injective and surjective, but just saying it's one-to-one just means injective. Now, one of the important things about bijections, which is going to come up a lot in chapter 8, is that having a bijection between two sets allows you to kind of compare the sizes of those sets. So to think about this, so let's think of a sort of example. So suppose that f from the set 1, 2, 3, 4 to the set B is a bijection. My question is now, how large is B? Okay, or in other words, how big is the cardinality of B? And if you think about that for a little while, you'll see that the answer is it's going to have to be 4, right? Because, for example, okay, f1, if I look at f of 1, f of 2, f of 3, and f of 4, those are 4 distinct elements of B because f is injective. So f doesn't map 1 and 2 to the same value, right? Or to the same element of B. It doesn't map 1 and 3 to the same element. You know, it doesn't map any two different numbers to the same element. So f of 1, f of 2, f of 3, and f of 4 are all different. So this implies that the size of B is at least 4 because it has to have 4 different elements. But it has to be equal to 4 because every element of B must be in the set of f1, f2, f3, f of 4 because f is surjective. So therefore, the size of B has to be 4. Okay, so this kind of gives you some idea about how bijective functions or bijections can kind of give you information about the size of a set. In particular, if there's a bijection between two sets, then they have to have the same size. So let's actually prove that formally now. So this is proposition 7.5.1. So here we're only going to deal with finite sets for now, but next chapter we're going to talk about infinite sets. So let A and B be finite sets. Then the size of A equals the size of B if and only if there exists a bijection from A to B. Okay, so let's prove this. All right, so first of all, let's suppose that there's a bijection from A to B. So we're proving this direction, right? So the second statement implies the first. So suppose there exists a bijection F from A to B. So then any two elements of A map to different, so maybe I should say any two different elements of A map to different elements of B, because it's, by injectivity of F. So what I mean here is, because it's injective, any two elements of A map to different elements of B, so therefore B must have as many different elements in it as A does. So the size of B must be at least the size of A. Also, every element of B is the image of an element of A. So therefore, the number of elements in B must be at most the number in A. So therefore, if there's a bijection between A and B, then the size of B must be the same size, must be equal to the cardinality of A. For the other direction, suppose that A, size of A equals B. Let's say that it's equal to some n, where n is at least 0. So we can label the elements of A and B such that, A is little a1 up to little an, B is little b1 up to little bn, and now we define f to be a function from A to B such that f of ai equals bi for every I between 1 and n. Now, perhaps I won't go into more detail than this, but it's pretty easy to see that this function is a bijection, right? So two different elements of A, let's say ai and aj, will map to bi and bj, which are two different elements of B. And clearly for every element of B, so if I look at bi from B, there's an element of A which maps to it, so which has, in other words, there's an element of A such that f of that element is bi, because you can just take ai. So that completes the proof. Okay, so let me just mention one more thing from the notes. So this is proposition 7.5.2. So it says that, so let A and B be finite sets such that the size of A equals the size of B, then a function f from A to B is injective or one-to-one. Maybe I'll use one-to-one. If and only if. So if I write this with IFF, this means if and only if f is onto. Okay, so the point is that actually, if you already know that the two sets have the same size, then actually being one-to-one is exactly the same thing as being onto. I think this is fairly evident, so I maybe won't give the proof right here. If you are interested in the proof, you can see the notes. But the point is, basically, if you already know the sets have the same size, and I map everything in A to a different element of B, then you're going to have to map something to every element of B. And vice versa, if I take the elements of A and map them to the elements of B, if you map to every element of B, and you know that A has the same size as B, then you must have mapped every 2 points to a different point of B. Okay. Okay, so the key things I want you to remember from this video are the definitions of one-to-one or injective, onto or one-to-one correspondence. So in other words, injective, surjective, and bijective functions. And secondly, you need to know how to show a function is or is not injective, surjective, or bijective. Okay? And if you're concerned that I didn't give you any examples where we were showing if things are bijective, well, that's because it's the same as showing something is injective and surjective. So if you know how to prove things are or are not injective, and you know how to prove that a function is surjective or not surjective, then you know how to prove that a function is or is not bijective. Okay, so I'll see you in the next video or in the next class. Bye-bye.